Does this work? Does the mic work? Does this work? Yeah, okay, so the mic works, nice. Okay, so this is basically gonna be I think the last episode of me explaining this Chatgpt module, and I'm not gonna write any code or something like that because I've already written the code and uploaded it to my website, and I think my website is gonna be linked down in the description below. So let's see if that is in fact the case or not. Yeah, it is. Okay, so nice. Let's just update that. Doesn't really matter. Nice. Okay, so basically I'm gonna explain the code here from my website. And the website is down in the description. You guys can check it out. It's basically just a detailed explanation of all the education and the work or the experience in the all the jobs and the organizations that I'm with and partnering with. But yeah, so this is more like you can see this as my portfolio, basically. So you can also check the course notes. I have written some course notes here, and this is just Haskell, electrical circuit statistics, discrete math, basic computer science, calculus, and also the documentation of the GPT-2 module that I actually is in my GitHub as well, and I think that is linked as well down in the description. But we have already explained all of this, and I think we ended with the, let's see, yeah, this forward function here for the block method. So now we have this whole GPT module class, which I'm gonna explain. And the first thing you guys can see that we have an init function which initializes the module itself. So this is basically the build blocks for the module, and all of these build blocks is basically based on the previous function that we created. So we initialize the module, and we also add the super.init, which basically reference the class to the nnn.module superclass, which is inside of PyTorch. This enables us to use a lot of different functions to do multiplications and math and stuff, so forth, which is super nice. Then we initialize a self.token embedding table, and I'm not completely sure what this does. So let's search this up and see what happens. It shouldn't be. Okay, so a simple lookup table that stores embedding and fixed directory and sizes. So this is basically creating a table for us. This module is often used to store word embeddings and retrieve them using indices. So basically all the words that we trained on in the previous functions is in fact stored in this table, or should be stored in this table. Then we have a positioning table. So we have words and positioning. So I think this is the amount of the words that we trained on that is gonna be stored. Say for example that you input a text into the GPT module, the words is gonna be stored in this table, and then the position of the words is gonna be stored in this table, I think. You can see here. So the positioning embedding adds positional information to the token embeddings, enabling the model to recognize token order. Exactly. So this basically adds the positions of the words that we inputted to the GPT module, and we also trained with. And this also maps each token in a vocabulary to a dense vector representation of size of n embed. So this basically stores the words, and this stores the position of the words. Right. So we have the words in the table and the position of the words in the table, basically. Then we create a number of blocks, basically, and this will create a sequential. So this will basically create blocks based on these parameters for each normalized layer, and n layer I think is a hyperparameter. So I can search for that somewhere. Yeah, so we have 4 in this case, in this example. So we have 4 n layers, which is a constant hyperparameter, which you can change if you want to increase or decrease the efficiency and also the accuracy of the module. And yeah, so this basically creates blocks based on the how many end layers we have, which is 4. So this will create 4 blocks in a sequential order. So this basically, so here's the layer of the words. This is the layer of the position of the words. This create 4 blocks basically, and then we create a normalized layer. So we normalize the values here in this layer, and then we have a linear layer, which basically is just a linear function basically. So it's nothing really that complicated, to be honest. And then we also self-apply self.init weights. So we start with the initialized weights to the module, which is super important. Otherwise, the weights would be either null or 0. I don't really know what default value the weights have, but we need to set initialized weight. And this is yeah. So this is basically this function here. And so this function basically creates, if this is an instance of the linear layer, we create a initialized normal layer, which the module weight, and the mean is 0.0, and the standard, what is this called? Oops. Standard deviation, basically. So this is the standard deviation, which is 0.02. So mean is basically the mean value of all the values, and standard deviation is basically the range if where the different values are. So say, for example, if we go to the whiteboard we had before, I can actually explain this. Start a whiteboard. See, nice. Okay. So I'm not really that good with writing with my mouse, but either way. So we have a coordinating system or coordinate system here. This is the x-axis, and the other one is the y-axis. Now they are not, they're not specifically named like that in the module, but we can do it just for sake of mathematical purposes. So we have an y-axis as well. So basically what, and this is basically linear regression. So say, for example, that we take in a batch in our system and we will get a point here. Jesus. Where's the eraser? Ah, here, nice. So maybe we can use this. Nope, that is a highlighter. Nope, never mind. Okay, so we have a point here, basically, and we have a point here, and maybe some points up here, maybe, and here, and there, and there. So basically, the mean value of this is just a straight line like this, basically. And so this is the mean value, and it initializes as 0, so it's going to be just a straight line in the x-axis. But the standard deviation is basically the distance between the mean value and these values. So the standard deviation is this length here, basically. Or the average length, which means that they add the length to all the points and then divide by the number of points, basically. And now what you have to take into consideration here is that the standard deviation is actually not a vector, or it's not a absolute value, which you may think because I write this as a distance, but it is actually a sum of points. So this is, they sum the amount of points here and then divide by the points. This can be a lot depending on how large the batch size is, basically. So I think the standard deviation is, I actually don't know the mathematical equation. You know what? I can actually look in the statistics, which I wrote here, and then I could, and the standard deviation should be actually written in here. Here, so the standard deviation. Now it's obviously not written exactly as I want to, but that's fine. So the standard deviation is basically, where's the standard? It's this one here. So this should be the standard deviation, but it's basically this one here. It's this function here. And the E is basically the mean value. So you take every point and to the power of 2 in the mean value, and then you have the mean value to the power of 2, and you subtract those two together basically to get the standard deviation. So this is basically the formula of standard deviation. Which is actually quite interesting. Yeah, I'm not going to go into that more. I will actually write a appendix for all the mathematical equations that we use in this module, and I will go over that too, but not today. So we set the standard deviation and the mean basically, and if the module doesn't have bias, or if it does have bias, we just initializes the bias to 0. And if we, so if the instance, if we have a linear layer, that's fine. So if this doesn't have it, if we don't have a linear layer, we basically instantiate the nn.embedding, which creates also a normal value, or a normal layer, or normalized layer with the mean of 0 and the standard deviation to be 0.02. So yeah. So this is a more complex function, but we can go through the, I would say, the more interesting explanation, I guess. So we initialize the class which we talked before. The vocab size is the number of unique tokens in our vocabulary, and we initialize a transform-based module with embeddings, transform blocks, and language module head. So here we map each vocabulary to this vector, which is this here. And this code here is basically this code here. And then we map the positions of the words. We add positional information to the token, yeah. So then we create blocks here. So a sequence of transform blocks that apply self-attention and feed-forward layers. And these blocks is basically based on this function here. And you can see that we use multi-add attention and feed-forward functions here, and also normalized layers as well. So we use all of the previous functions that we created before inside of this block, and then we use these blocks in the for loop that we had here. Then we create layer normalization, so normalize the final layer activations. So this is just a normal layer. And then we have language moduling head. So that we project the final embeddings to the vocabulary size for predicting the next token. Yeah, so this is basically just creates, try to predict the next token of the next position, basically. And then we have weight initialization. Initializes weights using Gaussian distortions. Now this can be seen as a blur effect, which is actually used in Photoshop, which is quite interesting. And it's technically, I think this is a convolution actually. Let's check that out. I think this is a convolution, which is actually really interesting, but that is a concept that I studied in a class in transforms and signals, which is actually really interesting. So let's see. We have a normal distribution. I think that is basically the same thing. So the normal distribution is also known as a Gaussian distribution or a probability bell curve. So the function basically looks like this here, maybe, or yeah. And here's the funny part. This normalized distribution is actually, I actually already defined the math for it. Normal distribution here. So this is basically the function that will be used in the GPT module. So we take in a value and then use this function. Now this will obviously be a loop, and we create a bell curve, which is a curve of probability. Then we have the definition of forward pass. So index is basically the input tensor of the token indices of shape B and T, where B is the batch size and T is the sequence length. Target token indices of the same shape used for computing loss, but we initializes that to none. You can obviously initialize that to something else. Yeah, so we basically print the index of shape, then we get the batch size and also the sequence length here. I think that was the sequence length, yeah. And then we calculate the token embed. So we just input it in a, so this will return a table basically, and of the words, and this will return a table of the positions, and we also add the device here and the sequence length as well to a tensor. So this will be a tensor of a table with positions. Then we add those two, so we will basically concatenate the words with their own positions. And then we input the words and their positions into the blocks. And then the linear layer, and this is here, this is where we actually use all the functions that we created. So we input a table or a tensor that is basically a table that has both words and positions. Now you have to take in consideration here that the words will be actually in a numerical value and not alphabetical value. And the positions is obviously the word positioning, I think. And then we have the logits, which this function is, and lm.head is just a linear layer. So if target is none, then loss is equal to none. Else, we get the shape of the batch size, the sequence length, and C is, I am not completely sure what C is. So let's check that out. Yeah, I think that is the loss, I think, or the cross entropy. Yeah. Then we logits.view, what this basically does. So we multiply the batch size with the sequence length to get the total batch size of the whole data that we inputted, and then we have the cross entropy and the logits.view. I'm not completely sure what that is. This was a very long time ago I programmed this. Given a tensor A with 16 elements in this case, to reshape the tensor to make a 4x4 tensor, we use a.view. So basically, we reshape the we reshape the matrix to a quadratic matrix here, basically. And then we do this. Then we do the same thing with the targets as well. And then we calculate the cross entropy here with the logits and targets. And what this function does, I think it's basically what it said, but I'm gonna look that up. So compute the cross entropy loss between input logits and targets. The input is a predicted unnormalized logits C-shape, and the target is ground truth class indices or class probabilities, which we used weights. It's fine. It returns a tensor, and the input shape is basically, this is a matrix, by the way. So C is the number of classes, and N is batch size. We don't use these parameters, so we're not gonna go through that. But then we'll basically return the logits and the loss. So we return a quadratic matrix and also the cross entropy here. Then we have generate. So basically what generate does is we have a hyperparameter that is called max tokens. And that should be up here, I think. Nope. Oh, it takes in the max tokens. And this will be a hyperparameter. It will take in a hyperparameter or just a value. You can define that however you want. And then we just loop for each max tokens. So usually I think in Chatgpt the max tokens is about 5,000 or something. I think you can change that. Let's see if that is correct. Max tokens in Chatgpt. Oh, it's actually 4,996 tokens. But that is for the 3.5 module. What is in the GPT-4? Okay, it's 8,000 tokens. We also offer an extended 32,000 token context length module, which we are rolling out separately to the 8K module. Okay, so it's either 8,000 or 32,000, which you probably will be using right now. And yeah, and then we just initial. So that is basically that. So I think for this sake here, or this example, we have let's see, should be okay. It's not a hyperparameter apparently. Okay, but that is the maximum tokens that you want to generate basically as text. And then we have logits and loss, which we will get for the self.forward, and index will be the input. And then logits is basically, here we take out some of the logits, and then we use the probability. So we calculate the probabilities with the softmax function. And here we have the next index, so multinomial. What this does is basically, see if I can search for it here. Yes, it's a probability as well, or distribution, yeah. Creates a multinomial distribution parameterized with total count either probs or logits, but not both. The innermost dimension of probabilities indexes over categories, all the dimensions over the index. So this is basically just creates a distribution. And then we concatenate the index with the probabilities basically. And I think that is basically all. So yeah, if we see here, iterative generation loops to generate max new tokens by predicting one token at a time. Then here we basically predict the current context, so get the predictions for the last token in the sequence and samples the next token using probabilities from the softmax and also the multinomial. Yeah, and then in the code we basically move the module to the device. We add a optimizer setup, so we can configure an AWW optimizer. This is basically a predefined algorithm that is already defined in the PyTorch module or PyTorch library. Specifies the trainable parameters of the module. So this will be module parameters and also the learning rate. And this learning rate is a hyperparameter that you can change. So sets the learning rate for optimization. So you might want to change this depending on how bad the neural network is actually. Then we have a training loop. So for each iteration in max iterations, this is hyperparameter. We basically create a periodic evaluation or evaluation. So if iter is equal to, and this is the, I think this is the percent sign is basically integer division. It will divide the iter with eval iters, and then if we get if that is equal to 0, which basically means that these two is almost the same, we whoops, that is not my intention at all. That's fine, I think. Whoopsie. Yeah, so we get the loss, so we estimate the loss. And then we just print the evaluation loss and the train loss, basically. Here we get the batch from train, and then we use the forward pass to compute the module's output logits and loss for the batch. Backpropagation optimization, so here we have a backpropagation. So optimizer 0 underscore grad set to none is equal to true resets the gradient to none to prevent accumulation for previous iterations. And so this will basically not take in consideration the history of iterations that the model uses. Then we have loss backward, computes the gradient of the module's parameters with respect to the loss, which basically means that we will do the module backwards with the loss, basically. So that is the backward iteration. And then we optimizer.step updates the module's parameters using computed gradients. So basically, when we have calculated the module backwards, we update the optimizer, basically, or the module's parameters using the computed gradients. And this is just printing the process, print the current duration number, process tracking, resaving the module, and yeah, that is basically all. I will do a more complicated explanation in terms of math later, and I will probably also write the math out before I even start to explain it, because it's a lot of explanations to do. So yeah, but I think that is basically all of this whole GPT module. The GPT module is out on my GitHub, so you can download and play with the code as much as you want. And you can also look through the documentation here on my website. Or will I? No, I will actually not publish the PDF. But you can look it through on my website. And the website will be linked below in the description as well. So yeah, that is basically the whole explanation. It took quite some time, but that is the explanation of the code. I will actually also create an explanation of the math behind it and try to see if I can visualize this in a graphical manner as well, to just make it easier for you guys to understand. But I think that is all, actually. So yeah, thank you guys for watching and have a great day.